usual level of the batteries. But now what happens when we connect in a series and parallel combination, right? And what is their effect, I would say, or what to do with the when we are trying to reach our particular voltage level of the battery pack. So here we are addressing how the series and parallel connection would work for. So I think no need to explain the what is series connection and what is parallel connection. It's a very generic and general. When you connect for the battery, if I correlate for the battery, if you connect positive to positive, right, and positive to positive terminal to positive terminal of the different battery and negative terminal of first battery to negative terminal of another battery, that connection we can call in a parallel connection. But when you connect a positive terminal of first battery to the negative terminal of second battery, that we can say as a series connection of the battery, right? And what happens in the series? Voltage is going to increase and current will be remain same, right, across the terminals. But if you look at parallel connections, even if you are connecting their positive to positive, negative to negative, overall the terminals end, if I look at the voltage would be remain same and then current is getting added, right? This is sort of effect of parallel and series connection is happening, right? Now, when we are going to select the battery pack, or I would say when you are going to build a battery pack, how we can construct, what is the minimum criteria or what is the start point we should go for? When we are constructing the battery pack, we should always use the NPMS theory. Now, what is meant by NPMS theory? So NPMS theory is nothing but a selection criteria or the first step when we are going to build the battery pack for the particular applications. And for any application, we very well aware about the power and energy requirement. These two parameters we already aware for the particular application. I know this power is required and that much of the energy that load will take, right? The second point, we should be aware about their operating voltage. And according to that, we need to build our battery pack so that we can reach up to particular voltage level. Here, the NPMS theory will help you out in that context. What is meant by N? So N is nothing but your number of cells connected in a parallel. M is number of modules connected in a series, right? So N parallel, M series, that stands with NPMS. The number of cells in a parallel, number of modules in the series, right? When you are trying to design or select the battery pack, rather than select, I would say the design or construct, right? You always first start to achieve the capacity and then go for the voltage criteria. When you are building a battery pack, always try to achieve the capacity first, the AH part first, and then reach out to the voltage later on. On the module level, it will be easy to construct the battery pack with this way. Otherwise, it would be quite challenging if you don't follow these rules for the construction of a larger battery pack. Would be quite challenging to meet the requirement. But if you, from the baseline, if you start the following the NPMS theory, which will be helping out to construct an optimistic battery pack. I have a good question for you related to this. I just wanted to understand the impact of these two, the series and parallel connection. Let's say, do you have one cell? A cell, right? Their characteristics would be like cell of 3.65 volt, right, as the voltage, and 15 Ah as in capacity. And this is in prismatic cell. And you are going to construct the battery pack. Now you have two problem statements. One, you need to construct the battery pack of 120 Ah with the as in capacity, and the voltage is 3.6 volt, right, for the particular battery pack. And second battery pack you need to form as a 15 Ah capacity and 29 volt as an voltage, right? These two battery packs you need to construct with by using this particular cell, right? Now, what is the input they have shared us? Voltage 3.65, current 15 Ah, length they have stated the physical dimensions of it, length, breadth and height 17 mm, 65.4 mm, 125.8 mm accordingly, right? Do you have calcs with you, the calculators? Can you find
Yes,
out?
yes,
Can you find out the
we have.
for this battery pack 120 Ah capacity and 3.6 volt as an voltage?
I believe 120 ampere hour divided over 15 because all of the batteries will be connected in parallel. All of the cells, sorry.
Okay. So let
Yes,
me
it
know
will
about number
eight
of
cells.
cells. So what you
8
need to
cells.
find, yeah, what you need to find here, number of cells you required and number of modules in that battery pack. You need to define these two things. How many cells you are going to use to build this battery and how many models you are constructing to build this battery.
Excuse me if I ask the question, what is the minimum number of cells in the module?
There is no criteria.
There is no criteria.
Yeah, there is no criteria.
So for me, for the first question, I would say one module with 8 cells.
One module with, yeah, it is fine.
It is simple, 8 modules in series, and for the second one, the 8 modules in parallel. Sorry, for the first one, 8 modules in parallel, and for the second one, 8 modules in series.
8 modules in the series and 8 modules in the parallel. See, if you considering the 8 modules in the parallel, so you are not following this rule. Module cannot be in a parallel. Module must be in a series.
So for the first one, as I said, it's 8 cells in one module.
Okay.
And for the second one, if I'm going to say it will be how much? 15 ampere hour. Okay, I will tell you.
It's 8 modules in series.
8 modules in a series for the second case, right?
Yes.
And how many cells in each module in the second case?
1 cell.
1 cell, exactly.
So say
yes. So if you look at the impact of your just series and parallel connection is reflecting here. The same cell, if you look at the quantity of the cell in the both the batteries are same, right? How you are going to define the quantity of the cell? Just multiply n into m, these two, right? Number of cells in each module and number of modules. So there are 8 cells only with these two batteries. Even their capacities are also same because we are using the same cell. So 8 cells, it's a just effect of your series and parallel connection that changes your voltage and then capacity, right? So the second battery can power your 12 volt load as well, even 24 volt load as well. But the first battery cannot power to your 12 volt load, cannot power to 24 volt load. But this will be last long for 3.5 volt voltage load, right? Because it's having a capacity of 120 Ah. Here it's only 15 Ah. So basically, if I go with the stepwise, you just need to do the simple calculation, write the NPMS theory. First, define the value of n. How? because n is number of cells, right? And which is going to be in a parallel way. So 120, right? This is in AH. So cells in a parallel, right? So, and we need to start with the achieve the capacity of the battery. So capacity is 120. So 120 divided by 15 leads to 8 numbers of cells. Now I just wanted to go with the modules. I want to go for a 3.6 volt as an voltage of the battery pack divided by the cell voltage, which is nothing but one cell is fine, right? Hence, we can say it is a battery with the 8 number of cells in a parallel in each module, and there is only one module, right? Second way, for the second battery, what we can say, again following the same theory, NPMS theory, defining the AH first, 15 divided by 15, 1. So one cell itself in each module. M is equal to 29 as an voltage divided by 3.65 is equal to about to 8, right? So we can say, hence it is a battery with a one number of cells in parallel in the module, and there are 8 modules in the series. Understood this? Because apart from this, I intentionally keep these cell same with these 2 batteries. For different configurations, you can plan for anything, but this is a very simple example. If you go for the larger battery capacities, then you blindly cannot move ahead. If you are not following this rule, it would be somewhere diverting you, right? So keep going with this model so that you will be easily trap your battery capacities and the particular voltage level, whatever you wanted to achieve for. So this is all about your battery, but technically you don't need to build a battery. You just need to select the battery for your application, right? But you should be aware what is the theory behind it, how they are going to approach. Is there any doubt till there?
No, it's fine. Thank you.
So a series parallel connection would be impacting your battery voltage level and according to your battery capacities. When you are going to try for a multiple batteries having their same voltage and same AH capacity, but the chemistry would be different, then your count of the cell would be different, right? That affects to your cell level the performance, like particular cell level voltage and cell level AH capacity. That matters when you are trying to calculate your number of cells. When you are going to evaluate the same chemistry and the same voltage as well as same AH capacity of the cell, then it must be equal number of cells in each batteries. When you're comparing these 2 battery pack of a same capacity, then it must be equal numbers of the cell, right? Now, the arrangement for the different cells to form a battery pack, right? There are different methodologies to install the batteries. Like instead of battery, I would say while creating the battery pack, right? There are four approach to go ahead for the mounting arrangement. The first one is snap in a mount. Okay, I'll explain their uses. Slide in a mount. Third, strap and lead mount, and fourth is your surface mount batteries for the cell when you are constructing the battery pack, right? Very common part is surface mount for your a large scale battery energy storage systems. Rest all other are very specific to the application point of view. Even I would say that these 4 are based upon the application point of view. Okay. Mostly you have seen these kind of structures for putting a cells, which was zinc carbon cell, right? The primary cell which we can use once and throw it out, right? those cells, if you look at this kind of system, snap in a mount for the mostly available in the power toys, right? Power tools as well as toys and remotes, right? The television remotes and AC remote, all those are having this kind of arrangement that we can say a snap in a mount. So based upon the application, it is going to be implemented. Slide in a mount, most preferred option for the electric vehicles, because for them, they need to draw out the battery pack for the maintenance perspective, as well as in case of servicing, right? And this is nothing but a slider they have provided to draw out your battery pack, right? Strap and lead is very specific to laboratory applications when you are going to be handling some testing of your PCBs and testing approach to the laboratory. So this is somehow having a proper notch and putting these two strips over your cell, and you are testing it out, right? When you are trying to even checking the multimeters and all. So this is most common for the laboratory purpose, the test lab and all. This is for your electric vehicles area. This is your power tools and remote, television remote and the AC remote, those applications. But this was most common for your cylindrical cell, right? This is based upon the application again for the EVs. Strap and lead mount is very specific to your the laboratory scenarios, whereas battery you cannot be packed, right? And having a mobility requirement. So you can easily use this with the leads and the strap. So this is very quite applicable in the laboratory part. But now if I look at the surface mount battery pack, this is very common for battery energy storage systems. If you look at a cell level, this is a cell which is just kept on a surface of this container. And this container is used to form a battery pack. Otherwise, you can set a cells on the surface and you can club it, right? And this would work. But the point is here, it's having a small container where you can keep these cells. So this is single cell. You can keep this cell and do the arrangement as per the requirement, like series and parallel connections. And according to that, you can draw out those leads here and you can use it. So this battery pack has been used for our battery energy storage system. The important point is their serviceability and no need to add additional parts. And this will be having a longer life because we are not drawing out every day, or I would say on the service time. Right. So these are very static in the application. So most preferred is surface mount. No need of additional structural arrangement for it. Right. Over here, if you look at the specific fixture is required to put your battery cells into particular this straps. So over here, this is not required. You just need to collect in electrical point of view, and then you can use the battery cells as it is. I have one picture to show you, which is one rack arrangement practically installed at one site. Battery cells we used from the lithium ion, and the manufacturer of the cell was LG Chem, right? And there were 14 modules in the rack. So if you look at this image, so this is a rack, whereas each drawer is kind of each module. So if you count it, there are these numbers of 14 numbers of modules are there, right? And this is a rack. Over here, there is a small BMS and protection circuitry, and it is going to be monitor and control to entire rack. And you can draw it out any rack as and when required for service, or let's say one of them is getting depleted more, so you can replace it. So it's a modular in the nature, right? So this kind of solutions you need to approach for your upcoming projects, whatever the assignments you are taking would be. So you can plan it such a kind of rack. So, or even if the manufacturer is not providing the same, you can ask him to customize it, right? They are definitely willing to do the same. Okay. If you use the LG cell level or the battery pack, so most probably they will going to provide this approach would be. So this is the very much clear approach towards their arrangement itself. So it's a physical environment which you are going to create for installing these two, right? Any query here?
No, everything is clear.
I have questions for you here. We are going to calculate the backup hour. Okay. Now, there are 4 different scenarios or the 4 different conditions. When you are going to calculate the backup time and you are don't have a clarity about the site scenarios and many other parameters too. So the first one, when there is only basic parameters you are aware, like battery capacity, battery voltage, and total operating load. So you are aware about these 3 elements. So how you are going to calculate your backup time of the particular battery for specified application? Does anyone list the formula? You have only battery capacity, battery voltage, and operating load. Can anyone list the formula to calculate the battery backup time?
For the first one, you need the backup type calculation.
Yes.
I
Right.
believe we can multiply the capacity by the voltage and then divide the operating load by
Okay. Correct.
them.
Correct. So you need to multiply voltage and battery capacity so that you will be getting your energy, right? VAH is nothing but your energy divided by your total load,
Yes, and
right?
it will give
So
time.
it
Yes.
will give the time,
Yes.
right? So it's a VAH divided by W. So in the DC, because battery is in the DC application, right? So DC side, your VAH is nothing but KW, right? VA is nothing but W. We can consider because there is no power factor. So WH divided by W, I would say if I look at the unit wise, so WH divided by W, so WW get cancelled, remaining would be H is nothing but time, right? So the formula would be battery backup hours is equal to your battery capacity into battery voltage divided by total load in the watt, right? Which will be giving you whatever the result would be in hours, HOURS, right? The time. Now, let's say you are stepping ahead and you already aware that depth of discharge. You are having here, you are having only these 3 parameters to calculate this backup hours. Now you want to calculate the battery backup hours when we consider the depth of discharge, including your all basic parameters like battery capacity, battery voltage, and total operating load. Now you need to consider depth of discharge. What would be the formula then? When you are going to consider the
Yes,
depth of
we will
discharge.
divide over the depth of the charge because I believe it will take more time.
Can you spell out the formula?
Battery capacity into voltage divided by load divided by
Load,
the
what's
percentage.
the depth of charge percent, yes.
Are you sure, guys?
Yes.
You need to know the effect of the depth discharge or how to
Correct.
calculate depth of
Correct,
discharge.
correct. Effective hours, I do want to calculate. Effective hours, I want to calculate. See, depth of discharge means, let's say 100% of the battery, let's say DOD is 80%, so I can use only 80, right?
Yes,
Then my time would be reduced, correct?
yes.
Backup hours would be reduced. Then what is the effect in the formula? Should I multiply at the bottom or should I multiply at the top?
Multiply
No,
at the bottom.
multiply it.
Multiply at,
For me at the top.
for you at the top. For Kabilan, for you at the bottom.
Yeah, I was thinking at the bottom.
Yes, and the
Saha?
bottom, yes.
So you are wrong, guys. Multiply
bottom.
at the top because it's in a percentage.
Got it.
See.
Okay.
So you got the battery capacity. Now the capacity is initially 100%, but when the parameter comes as the depth of discharge, so the 100% is not there now. You are getting whatever the DOD they are saying, like they are saying 70%, means out of that 100, you can only use the 70% of it. So it must be multiplied at the top. Got this?
Yep.
Now, one more point. Let's say you are having depth of discharge in place, battery capacity, battery voltage, load. And now you are adding your charge discharge efficiency over there. Okay. Now the input is clear. We when we are considering the depth of discharge and your charge discharge efficiency, including your basic parameters like your battery capacity, battery voltage, and total operating load. Okay, what would be the formula? How you are going to calculate? You are having a charge discharge efficiency in place. And you want to find the effective battery backup hours. What you will do?
It's also a
Multiply
percentage
by,
like the
Yes,
DOT.
multiply by the efficiency.
Multiply at the top.
Yes.
Saha,
Yes.
for you,
Yes.
Kabilan, should I multiply or divide?
Multiply at the top. Since it's
Multiply.
efficient.
It's an efficiency. Okay, you all are right, guys. So when you are going to calculate your battery backup hours, considering your battery capacity, battery voltage, total operating load, depth of discharge, and charge discharge efficiency, then it would be this formula you need to use, because see, look at, these are the very basic things. We just added these two over here. DOD we should multiply it at the top. This value in a percentage, okay, percentage. So when you are writing 80%, so don't write 80 itself, write 0.8, okay, or 80 divided by 100, right? Because it is in percentage. Now, what is the effect of state of health? When you consider the charge discharge efficiency, state of health, depth of discharge, including your basic parameters like your battery capacity, battery voltage, and operating load, what would be the formula? And this, if you are considering the state of health of the battery as well, what is the resultant formula you are going to use in the field?
So again, state of health is
Shall be
equal-
multiplied.
Yeah.
It must be multiplied at the top, right?
Yes.
Exactly. Because if you look at all those effect of depth of discharge, charge discharge efficiency, and state of health, all three parameters are reducing your battery capacities, right? And that's why I would say reducing the effective battery capacity. Okay. And that's why you need to multiply these three parameters to the top of the formula. Got it? Now, if I give you one example to define the battery pack and their effective backup hours, are you going to calculate the same? I'm
Yeah.
having a problem statement, guys. Just note it down. Battery capacity of 1000 Ah, battery voltage. What voltage you are going? 240 volt, okay, or 24 volt. Okay, battery voltage is 24, battery capacity is 1000, and your load is 100 watt. Thousand Ah multiplied by 24
240 hours.
divided by load is 100. So here your battery backup power would be 240 hours, right? Now just consider depth of discharge of 80%. What would be the effect of battery backup hours?
192 hours.
Instead of 240, it goes to 192. Now again consider charge discharge efficiency of 92%.
177.
177. And consider now it's a 2 years long operating plants, and it has already 2 years old. So it's a state of health. You just need to consider the 92% again, or the 90%.
159.
150. Now just mark the times over here and just correlate how the impact is happening. Because at the top you are having the theoretically the same battery pack, but the impact of your DOD, impact of your charge discharge efficiency, impact of your SOH is drilling down your overall backup hours, right? Initially it was 240 over here, right? Here something 192. Here 180, how much it was, Kabilan?
179. I think.
179 something, right? And at the last 150,
I think 159. something like that.
150 and whatever it is, you let the take out this. But if you look at on the first day, it might give you the 240 units or 240 hours backup. But if I consider the depth of discharge on the first day, it can give me 192 hours of backup time. Now this I can extend up to this, but it is going to be a 0% of balance in the battery then, right? So SOC would be 0%. Then I can reach up to 240 hours of backup. Here SOC would be 20%. So after 20%, I need to start the charging of the battery. SOC is 20 means your DOD goes to 80% itself, right? That is what you considered for. Next to it, when you are going to be charging and discharging perspective, it is again, because of that efficiency, it is again down 179 something. Now, if you consider the plant is 2 years old or 3 years old, according to that, the state of health, the parameter coming from your BMS, right? We just need to multiply that. Then again, it will give you the effective battery backup hours. Have you got it?
Yeah.
Any queries here? Any query till now, guys?
No, it's fine.
No? Yeah. And these are the formulas which you need to use for your applications when you are planning for your battery pack, right? And across the, let's say, 10 years life you are calculating, or 25 years of the plant, you need to think upon that. Battery capacity needs to be planned for end of the life, right? And according to, you need to just map your battery pack. So till now, so this is your completion of module 3. Do you have any queries? Just let me know. We'll continue. Before that, we'll have question answer sessions. Let's say module 1, 2, 3. Apart from these 3, do you have any questions to these modules? Let's discuss on it and then we'll move ahead. Do you have any queries, any problems, any questions in the module 3?
I think I'm good on mine.
Okay. So see, module 3 is very specific to the batteries. So till now, if I revise it, so